This is the second part of two parts for the acid-base notes. And we left off with this slide, slide 43. And so I'm going to show you the answers for this so you can check your notes just to make sure you have them. So if for some reason yours don't match these, you should probably ask a neighbor, a friend, or me what you did wrong, okay? Because you're going to have to replicate problems like this on your test. All right, let's move on. So we're going to talk about some neutralization reactions. And that's how we started these notes off last time, with a question about a neutralization reaction. And that is when you take an acid and a base. In this case, in this animation, you've got hydrochloric acid and sodium hydroxide coming together and forming two new substances. And these substances, by definition, are always the same types of substances. So we're on slide 45 right now. So the general reaction for neutralization is you take an acid and you mix it with a base and you get a salt and water. The key component here is this A, because if I had just put salt, you would think sodium chloride, because most people think that. But we should know from last semester that salt refers to any cation and anion combination, well, not any, but most cation and anion combinations, ionic combinations. It's a double, it also can be called a double replacement reaction because you're just swapping the parts. It's like two couples dancing, remember, and then they switch partners, okay? So an acid and base reacting together, making an ionic salt and water as the product. Now, salts can be acidic, basic, or neutral, depending upon how strong or weak the acid and base is. So if you are chemically bonding a strong acid and a weak base, the salt's probably going to be acidic. If you are chemically bonding a weak acid and a strong base, the salt's probably going to be alkaline or basic. So neutralization, even though it's called a neutralization reaction, and the word neutral is the root word, doesn't always mean that it's going to end with a neutral pH of 7. It's probably going to be skewed one way or the other. You would have to have equal ionization of both the acid and the base to get a perfect neutral pH quantity. So pH factor, you've heard this before. It's typically, most people would the first thing that pops into their head is like an advertisement for shampoo or skin products. Oh, it's got a pH factor of yada, 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 you know? But what does that mean, okay? It just means the pH number, that's all it means. Is it balanced, you know, or not? So, like I said before, if you have a strong acid and a strong base, if they're equal in concentration, you're going to end up with a neutral. If you have a strong acid and a weak base, you're going to end up with a pH less than 7. And on the opposite side, a weak acid and a strong base, you're going to have a pH greater than 7, which I just said previously. And then a weak acid and a weak base, finally, the pH is going to vary. It really depends on, it could be neutral again, if they're equally weak. But it's going to vary. So what's a salt? We know this. We know what a salt is. This is old news. Ionic compounds made from the anion and the cation. The anion comes from the acid and the cation comes from the base, okay? Because we know hydroxide is the negative part, OH minus, and that's a base. So therefore, the cation has to come from the base, okay, the positive part. I'm just making sure you got that down in your notes. These notes are very short today compared to what we already did. So predict the products of each neutralization reaction. This was the very first one that you saw on the very first opening slide to part 2 notes. This hydrochloric acid and sodium hydroxide. So if it's a double replacement, that means that the cation from the base is going to hook up with the negative from the acid. Which one of these is negative? Right, chlorine is -1. So you're going to get sodium chloride, and what's HOH? That's water. Every time it's a salt and water, okay? How about this one? This is acetic acid and potassium hydroxide. Potassium is the cation, so that's going to hook up with this acetate polyatomic ion, and that hydrogen is going to go to the OH to make water. So you should write those down in the blanks, okay? It's a double replacement, but your products are always a salt and water, okay? But make sure you get the salt correct. This polyatomic ion does not break up. Okay, how about this one? So now you're going to have to probably go back to these later and determine, using your knowledge and your skills from last semester, what is nitrous acid? I guess you could look it up. That's fine with me, but as long as you know how to. Not nitric acid, nitrous acid, and calcium hydroxide. Calcium hydroxide, I believe, was in our notes from last time. So if you could just turn back a page or two, and you'll find that and under strong bases. And write down the proper products. Balanced reaction, okay? And then what acid and base would form sodium fluoride and water? So now you're going backwards. You're given for number 4, you're given the products, and you have to double replace them, okay, in a reverse neutralization reaction, and determine what the acid and the base would be, okay? And then on the final one here, which somehow is irritating Einstein, I don't know why that's there, but what acid and base would form potassium nitrate and water? So this one's a backwards one also. So you are determining you just take that cation, that potassium, and that polyatomic ion, nitrate, and take the hydrogen and the hydroxide from the water and replace them, okay? Okay, so this is going to lead us into our next activity, which is going to be a lab grade. It's going to be a gizmo, a virtual lab, on this subject called titration. If we had an actual laboratory with actual equipment, and it wasn't, COVID, we would do a lab like this most likely, but we'll do a virtual one instead. It's easier for everybody that way. So this is a method for determining the concentration of a solution by reacting a known volume of that solution with a solution of known concentration, okay? So This is the unknown. This is an acid of unknown concentration. So I want to determine what the concentration is. So I take this volumetric burette. It's just kind of a tube that has graduations on the side of it and a valve. And I put in a known concentration of base. And they are different colors. There's an indicator in here, which I'll tell you in a minute. And you open this up and you drip, drip, drip the base into the acid until a color change occurs. And in that process, you are measuring precisely how much, what volume, volume of that solution you put into it. And you can do a little bit of math, and then that tells you what the concentration of the acid is. Because when it turns colors, that means it is neutralized. Pretty cool. So here's the steps for this process. So one, you take a measured volume of an acidic solution of an unknown concentration, and you put it in this flask. This is called an Erlenmeyer flask. It has a flask that's flat on the bottom. There's another kind of flask that's round on the bottom. Some people may just call that a round bottom flask, but it's also called a Florence flask. So this is called an Erlenmeyer flask. And you put an indicator in there. It's kind of like a catalyst, but it doesn't take part in the reaction, but it just serves as an indicator. It changes color when it reaches neutral. When it neutralizes, it changes color. When it reaches a pH of 7, it neutralizes. And then you fill that volumetric burette, it looks like this, with the what's called titrating solution. And that's your base. And you can read the volume on it. And then you put measured volumes, so like 1 milliliter at a time, or and a couple drops, 1 drop at a time, and you're measuring the volume as it goes. You know your starting point and your ending point. And then once that equivalence point is reached, the color will change. See, it goes from blue to red, and you'll know. Sometimes it'll turn red really quick and then go back to blue. It's not quite there. It's almost there. And usually there's this little magnetic stirring rod on the bottom that's spinning around and spinning around, mixing it. So it mixes. So it mixes it properly. And then when it stays red, you've hit the equivalence point, and you know that you have reached neutralization. And then, like I said, you can do the math. And you're gonna see how this works with the virtual lab in the Gizmo. And again, this is how you set it up. This is the diagram. This is what it looks like in reality, and you can see the color change. So in this case, this solution's clear, not blue. And then you can see it changes color maybe after a few drops, or many drops. It doesn't stay pink. Once it stays pink, once the color change is permanent, then you have neutralized the acid and you can figure it out, okay? All right. And here's where it all ties together, of course, in something mathematical. And this is a rather complex series of steps to determine, so using titration data to determine molarity. So remember, that was the concentration. In our last set of notes, I gave you 2 examples, 0.1 molar of acid versus 12 molar of acid, okay? So we're gonna use a very simple formula, but this is gonna teach you the process, all right? So, and this is exactly from your textbook. So even though it's in your notes, you could also look in your textbook for more help if you needed to. So we're gonna go over this in detail, all right? So let's imagine you have a volume, because there's gonna be a question like this on your test. Let's imagine you have a volume of 18.28 milliliters of a standard solution of 0.1 molar sodium hydroxide, okay? That's how much of it was needed to neutralize 25 milliliters of methanoic acid. Now you see, you don't know what the molarity or the concentration of this methanoic acid is. It's unknown to you. But you did titration. You took a known solution, a known molar concentration of a base, and you dripped in 18.28 milliliters of it. And then the color changed, okay? So technically you mixed 18.28 milliliters of base, sodium hydroxide, with 25 milliliters of this acid, methanoic acid. How can I use this information, this titration data, to determine the molarity or the concentration, which is the same thing, right, of this acid now? And this is the math part I told you about. So first it's the process. First it's the physical process of dripping it in. And once you get that volume, you can use this information, volume of substance A, volume of substance B, moles of substance B. What are the moles of substance A? How do I determine that? So you've got your knowns from the problem and your unknown. Okay, so how do you solve it? You have to write a balanced chemical equation. Oh, boo-hoo-hoo. Yes, you do. It's very much in line with stoichiometry, where you need to have that information first. But we just did some of these. You just showed me that you could take a base and an acid and turn it into a salt and water, okay? So I think you have that down. Then you convert the because they give you milliliters in the problem. But this problem, this formula, molarity is given in moles per liter. Exclamation, okay? This could totally throw people off when they're trying to solve problems. So you have to make sure that your volumes, when you're doing this math, are in liters. Just like when you were doing the gas laws and they had to be in certain units, had to be in Kelvin, not degrees Celsius, had to be in liters for the ideal gas law, not in milliliters, right? So you have to convert your volumes to liters. So we take our volume of B and we convert it to, simply because 1 liter is equal to 1,000 milliliters, and the milliliters cancel out and we divide, and that just means the decimal place moves over 3 places, 1, 2, 3, and we've got 0.01828 liters of sodium hydroxide, okay? All right, that's slide 54. Slide 55. So then we calculate the moles of sodium hydroxide. Now we can do that because we have the molarity, which was given to us right here. Molarity, okay, multiplied by liters, and the liters cancel out, giving us the moles of sodium hydroxide. This is how many moles we have. 1.828 times 10 to the negative 3 moles. Okay. Then we calculate the moles of the other substance. So how do we do that? Balanced chemical equation using the mole to mole ratio. Man, all that stuff that we learned is being applied here, isn't it? Okay? And you always have this problem to go back to and use as a sample, as a guide, all right? And of course your textbook. So we take the moles of sodium hydroxide, we multiply that, and it's a 1-to-1 ratio, so it's pretty straightforward, but you wouldn't know that if you were just guessing, so you had to have the balanced chemical equation. And so we know the moles of sodium hydroxide cancel out, leaving us with the moles of the methanoic acid, and now we've got the moles of that. And now we can calculate the molarity. So we've got the moles of methanoic acid equals the molarity of A times the volume of A. And so, again, we have to convert that volume into liters, otherwise it won't work, okay? And we just divide those two numbers, moles per liter, because molarity is in moles per liter, How do we know that? I mean, it's here, it's in the problem, okay? Although it's in our notes as well. We took the notes on the first part of these acid-base notes, okay? And when we divide these two numbers, we get 7.312 times 10 to the minus 2 moles per liter. And that is it makes sense, okay? And it's in the right units, okay? So, now your job is, for the remainder of this class, this is pretty much all you have to do, is answer this practice problem, which is virtually the same kind of problem as the sample problem that I just gave you, okay? So what is the molarity of a nitric acid solution if 43.33 milliliters of 0.10000 moles, not moles, molarity, concentration, potassium hydroxide solution is needed to neutralize 20 milliliters. So it's the same problem. You just have to plug in all the steps, okay? So you guys work on that. Let me know if you hit any snags. Let me see, I don't think that, yeah, I do give the answer in the notes. So, but you can check that with me later. So when you get the answer, come check it with me, okay? And that's why the little froggy is at the end of your notes. All right. Have at it.